So what we covered in the last part was that we could write cosine of theta plus or minus alpha as cosine of theta, cosine of alpha, and then minus plus, so corresponding to whether it's a plus or minus sign. And this is sine theta, sine alpha. And then we also had sine of theta plus or minus alpha equals sine theta cosine alpha, and then, but this has a plus or minus as well, and this is cosine theta sine alpha. In maths and physics, or in general science courses, what you want to do is to be able to find multiple ways of achieving an answer. So it's not always possible, but where it is possible, this should be strived for. So another way we could look at this is through matrices and how they work. And so we have a matrix acts on some vector v, and it might produce some other vector. Let's call it q. So this m projects or maps this vector v to the vector q. And what we could do in these cases is say, well, imagine I had an axis, a y-axis, and an x-axis. And then we have some vector that we'll call p. And then m acts on this to make an image of p somewhere else. So it might do some operation and it might put p here. So the image of p we'd call p prime. So what it might have done, it might have reflected it, it might have rotated it, it might have done a bunch of other transformations, and it would have got it to this image. So it's mapped p to point p prime. But what we want to focus on is how we could represent a possible rotation matrix and how this is helpful in determining these double angle formulae. So what I'm going to do here is I'm going to write out, let's say, a general 2x2 matrix. So M equals A, B, C, D. And then we're going to call X in its own basis. This is 1, 0. And then Y in its own basis, 0, 1. So let's say what I want to achieve from this is to find a rotation matrix that tells us what our image is after we rotate by a certain angle theta. So if I do M on X, this is A, B, C, D with 1, 0. And then using how matrices are multiplied with vectors, so we have here A times 1 and then plus the B times the bottom 0. And then we have C times the 1 plus D times that bottom 0. And this is just AC. Now notice this is just, AC is just the first column of this matrix. Now what happens if I act with M on Y? This is A, B, C, D. This is on 0, 1. So we get A times the top 0 plus B times the bottom 1. C times the top 0 plus D times the bottom 1. And this is just equal to B, D. Now notice this is just the second column of this matrix. So what this means is when I operate or I apply this linear operator, so M, this matrix, to either X or Y, or the 1, 0, and 0, 1 vectors, I just get out the first and second column of the matrix. So if I want to find how to represent a rotation matrix, what I could do is I could act it on my X and Y coordinates, and then I know the image when I rotate a vector 1, 0, 0, 1, because we can work that out from using the unit circle, we can then say these are the columns that are in this rotation matrix. So let's go a bit more into that. This is X, this is Y. So imagine I have a point on here. So this is the point 1, 0. And I rotate it by an angle theta anti-clockwise. Well, we know what happens when I rotate it anti-clockwise by theta. We get an x coordinate of cosine theta and a y coordinate of sine theta. So again, you can see here that this part will be sine theta, because by definition, this is the y coordinate, and then the adjacent term, or the x coordinate here, would be cosine theta. So what we've got here is that the image, so this matrix R, when acting on 1, 0, gives us cosine theta, sine theta. So the first column of R of theta must be cosine theta, sine theta, and then this is B and D, which are still to be determined. So we know that when we rotate the x coordinate, or this point 1, 0, by an angle theta, we get this image, cosine theta, sine theta. So this must be the first column of our matrix. Now, what happens when I rotate the vector 0, 1 by theta anti-clockwise? Well, let's have a think. We know that the new x coordinate will be in the negative direction, so it'll be here. And how much of that is here? So if I were to compare it to here and draw a little triangle, we can see that this is sine theta, but in the negative x direction. So r of theta on y, so I should use the notation x hat and y hat like I did before. So r theta on y will give a minus sine theta for the x coordinate, because it's sine theta here, and that's in the negative x direction. So I emphasize here. But then its y coordinate will be a cosine term, because notice its y coordinate is adjacent to the angle, and it's in the positive y direction. So it's cosine theta here. So it's cosine theta. And we know from earlier that the image of y, when acted on by this, must be the second column of the matrix, so B, D. So now we can complete our picture for r theta. This is equal to cosine theta and sine theta, and this part must be minus sine theta and cosine theta. So this is our rotation matrix, and it rotates a vector or some point by an angle theta anti-clockwise. Now, how can we get r of theta plus alpha? Well, surely that would just be substituting theta plus alpha here. And this is cosine of theta plus alpha. But another way in which we could do that is that we could say that r of theta plus alpha is just the same as r of theta times r of alpha. Because if I wanted to rotate by theta plus alpha, I could firstly rotate by alpha and then rotate by theta. Or I could rotate by theta and then by alpha. So this should also hold, because we know that if we rotate by a certain angle, we could just break that down into smaller rotations. So r of theta plus alpha is equal to these two expressions. Now, if we act on a certain vector, let's call it v. Now, I'll choose to write this as r of theta and then r of alpha acting on v. Again, I could have chosen the other way, but it doesn't really matter here. It's just to show you that what we could see this as is an r of theta acting on v, so it rotates firstly by theta, then by alpha. And so because I've got an expression for this rotation matrix, we can now find a way to relate some of these sine theta plus alpha and cosine theta plus alpha terms. So what I'm going to do is just a case of simple algebra and matrix multiplication. Got that r of theta plus alpha equals r of alpha times r of theta. And this is just going to be equal to, well, using our expression for r of some angle, it's cosine of alpha minus sine of alpha, and then cosine of alpha. And then this part is cosine theta, sine of theta, minus sine of theta, sorry, sine of theta, and then cosine of theta. And then all we need to do is multiply like matrices. So if we wanted our first row, first column, so that is cos alpha times cos theta. So I'm going to write it in this way to get it in a more similar form to what we're used to. So cos theta times cos alpha, and then we've got the minus sine alpha times the sine theta term. So that's minus sine theta sine alpha. Now if I wanted our first row and second column, then this is cos alpha times minus sine theta. So I'm going to write that as minus sine theta cos alpha. And then we've got minus sine alpha times the cos theta. So I'm going to write that as minus cos theta sine alpha. And then for the bottom left, so that's second row times first column. So that's going to be the cosine theta sine alpha, and then the cos alpha times sine theta, which again, I'll write it in this way. And then the final term, second row, second column, that's minus sine theta times the sine alpha, and then the cos alpha times the cos theta, like so. So this is our expression for r of theta plus alpha, because it's made up of the two rotation matrices, theta and alpha. Now, if we just match these, we can see that this part, the top left, this must just be cosine of theta plus alpha. And then this part must be sine theta plus alpha. This top right must be minus sine theta plus alpha. Notice it's exactly negative of the bottom left. And then this part is just the same as the top left, but written in a slightly different order. So we found expressions for cosine of theta plus alpha and sine of theta plus alpha. And so we found a rotation matrix that uses these properties to help us identify a trigonometric identity or relationship. Now, what can we do? It's always interesting to see what can we do with these properties that we found and this new information that we've learned. Well, one thing is we could say that r of theta 1 plus theta 2 plus theta 3. Well, we could break that down into r of theta 1 plus theta 2 times r of theta 3. Or if we wanted to get it all as individual rotation matrices, so it's r of theta 1, r of theta 2 times r of theta 3. And then we could write an expression for r in just the first term. in terms of theta 1, theta 2, and theta 3. And the other, we could multiply these individual rotation matrices, and then we can find a triple angle identity. So I'm not going to bother with that because it would just take too long. But you can see that we could generalize to higher and higher rotations, or more and more rotations in these problems. And it's a key skill that you want to use when you're doing maths, physics, chemistry, any types of problems, even in engineering. You want to be able to write an expression one way, and then also find an alternative route for finding that expression. And then when you relate those together, you then find an identity or relationship, and then you can use this to learn even more information throughout a question. So the primary mechanism through which you solve problems is always to try and find one way of doing something, then another way of doing something, relate these two, and then use the properties of what you found and different ways of expressing something. So how you look at a problem, how you see the way in which to get to a solution or find a relationship, that will help you determine properties later on. It's really that simple. Obviously questions might be difficult, but what you're trying to target remains the same in nearly every problem. And another thing that we could look at here is that if I had r of theta, so actually I'm going to start with r of minus theta, and then r of theta. I want you to have a think about what you should get from this result. So we always read from right to left when multiplying matrices. So I've rotated something by theta, and then I've rotated it by minus theta. So what matrix should I get in the end? Well, let's write this out explicitly. So this will be cosine of minus theta minus sine of minus theta. This will be sine of minus theta. This will be cosine of minus theta. And then here we have cosine theta minus sine theta, cosine of theta. Now what we want to do is we want to simplify the minus theta expression. And what we can do is we could use the unit circle to say that we know theta is measured anti-clockwise here. So if I were to measure minus theta, so it's going theta the other way, so going clockwise, well, the x coordinate is still the same. It's only the y coordinates change. So cosine of minus theta, the x coordinate, is still the same as cosine of theta. But then sine of minus theta is actually minus sine of theta. Because if you look here, the x coordinate is the same for both, but only the y coordinate has changed. So that's sine theta originally, now it's minus sine of theta. And we could also have seen that from when we draw our our cosine and sine graphs. So cosine looks like this, it's symmetric. But then sine is anti-symmetric. So it looks something like this. So it looks the opposite as it does on one side compared to the other side. So if we put all this in, what we've just got here is that we've got cosine theta. This will become plus sine of theta. This will become minus sine of theta. This will become cosine of theta. And then this part is still cosine of theta, minus sine of theta, sine theta, cosine of theta. So multiplying these together, we have first row with first column. So this is cosine squared theta and then plus sine squared theta. And then we have first row with second column, so that's cosine theta times minus sine of theta. And then the other one is plus sine of theta times cosine of theta. But this is just 0. And then this part is minus sine theta, cosine theta, plus sine theta, cosine theta. This is just 0. And then second row, second column, this becomes sine squared theta. So minus sine times minus sine, and then cosine times cosine. And then we can use the fact that cosine squared plus sine squared is 1 to write this matrix as 1, 0, 0, 1. So I'll write that further down just to emphasize. That's 1, 0, 0, 1. And this is just the identity matrix. So you sometimes see it written as this as well. And this identity matrix is just a do-nothing matrix. It does nothing. So if you look at the first column, if we started with a vector of 1, 0, when we act with this identity matrix, it just gives us 1, 0. And if we acted with 0, 1, it just gives us that second column, which is 0, 1. So it does nothing to any component of our vectors. This is just the identity matrix, which is what we expect. If I rotate by theta, and then I rotate backwards by theta, then I'm going to have done nothing. So the image will just be the same as the original starting point. Now, we would expect the identity matrix, and you could try this for yourself if you had r of theta, and then r of 2 pi minus theta. So this is rotating by 2 pi minus theta, and then rotating by theta. So this will be the same as r of 2 pi minus theta, and the r of theta. And this should also equal the identity matrix, because in total you've just rotated by 2 pi, which does nothing. And then you could check this by saying that this is equal to r of 2 pi if you add those two angles, and then substituting 2 pi into our rotation matrix, so r of 2 pi, we get the identity matrix. So you get the same for 4 pi, 6 pi, everything in that manner. And then the final thing to note is that we've looked at rotating a point here. Let's say I had a point on here and I rotated it by let's say I rotated it by an angle alpha. So my new point is here. So let's say I rotated a point by an angle alpha. Well, what I could have done is if I started with a point at that axis, so let's say it's on the x-axis at the moment, what I could have just chosen to do is rotate the x-axis by an angle alpha, but the other way. And what I mean by that is that the coordinates of this purple point in my x and y is the same as if I'd just rotated the x-axis and y-axis by alpha clockwise. So rotating that point anti-clockwise is the same as keeping that point there in the red, at the red point here. So I could have kept that point red here, and then rotating my axes by alpha the other way. It's the same thing, it's just a different perspective. As in, if someone's traveling 5 meters per second faster than you, you could either see it as them traveling 5 meters per second faster, or you traveling 5 meters per second slower. So in a reference frame, you wouldn't know which, you wouldn't be able to distinguish. You could only tell that someone is moving 5 meters per second more than the other. So this is the same as that relative motion. I could either move my point in red by alpha anti-clockwise to become that point in burgundy or pink, whatever that color may be, or I could keep the point fixed at the red coordinate here, and then I could move my x and y axes by an angle alpha the other way. And what we learn from that is that my x prime and y prime axes from the previous video, so I've had x prime hat, well, that is just the x-axis rotated by alpha clockwise. So that is rotating by an angle of minus alpha, the x-hat axis. And then we could say the same for y prime. Y hat. Or another way to see it is if we rotated the x prime and y prime axes, then we'd get x hat is equal to r of alpha, x prime hat, and then y hat is equal to r of alpha, so anti-clockwise by alpha, of y prime hat. And if you put these expressions, you get exactly the same thing that we did before. So we would have gotten that x hat is equal to cosine of alpha minus sine of alpha, sine of alpha, cosine of alpha. And then on x prime hat, this axis would have gotten us some expression in x prime or y prime. So in x prime hat term, this would be the vector 1, 0. So in x prime hat, 1, 0 here is written in the x prime hat basis and y prime hat basis. And so what we get there is that x hat is equal to cosine alpha times x prime hat. And then we also get that it's equal to plus sine of alpha of y prime hat. Because what this expression gives us is cosine alpha and sine of alpha. And these are still in the x prime hat and y prime hat bases. So because we know x hat is 1, 0 in its own basis, what we've just done here is that we've said that we want to get the x hat axis in terms of the x prime hat axis, and it's just a rotation of the x prime hat axis by an angle alpha. So we wanted to write any coordinate x. So we wanted to write the x hat vector in terms of x prime hat vector. It's just a rotation of this vector. And this is how we get an expression for these. So as you get more comfortable with these manipulations, you'll be able to see how different parts of linear algebra are connected with these double angle formulae that you would have learned. And you could extend this to further and further rotations or other operations and seeing what properties you can determine from these. If you have any questions, please let me know. Hopefully all that made sense, but if there's anything that was unclear or you thought not explained as well as it could be, please do let me know in the comments.